Okay, let's have a look at the two papers describing the Kraken software tool and also the Bracken software tool. These are two independent tools, but they are made by the same people, more or less, and they are often used together, as we will see. So let's start with this Kraken software first, and the paper we are looking at is actually for the original version of this software. Later it has been extended in two different directions actually. So the software we use in this course is called Kraken 2, but it's the same idea. It's the same idea. So what is new in this second version has something to do with memory and speed, and the basic idea is the same. So let's have a look. First of all, this is all about taxonomic classification, right? So we have a set of reads, and this could typically be Illumina, paired and short reads, but not necessarily. It could also be all kinds of reads, really. It could also be nanopore reads. It's not really that well documented if this Kraken is well suited for nanopore long reads, but at least it's possible to use it. There is no sort of, should I say, technical reasons for why you cannot also use Kraken on nanopore reads, but it might not come out that successful. And all kinds of other reads, right? Whether it's single or paired end doesn't really matter. The only difference is that if it's paired end, the pair of reads is classified together as you should expect, right? But reads of any kind. Okay, so we want to assign each read or read pair then, if it's paired then, to some taxon. And this means actually assign it to some tax ID, right? I use this phrase here because this is how we call it in my documents. So this is the tax idea. That, for instance, the NCBI taxonomy database has a tax ID for each taxon, right? And let's now focus on how the idea is behind this tool, because there's a lot in this paper about the implementation of it. How to do this very fast and with as little memory as possible, but this is sort of too technical for us now. We will not dig into that. I just say that these are important topics. It's not like I leave it out because it's not important, but first we should understand the idea, and then we can start working on this more technical part of it. So for BIN310, we are satisfied by understanding the idea. Now this is a figure I've taken from that paper. It's actually the first figure. And this explains a lot of it. But it's not so easy to understand this figure once you see it, because it appears rather at the beginning of the paper. So what I suggest now is that we try to dig a little bit more into what is happening here, and then we return to this figure, and then we understand what it means. We can see that there are some reads and some k-mers up here, and there is some taxonomy tree here, and there is some classification path or tree over here. Yeah. So let's see if we can understand this idea first. And I would like actually to start by how Kraken is building the database. Because any taxonomic classification requires that you have a database. You have seen some genomes before that you know the tax ID for, right? And then when we have a read now, we want to see if we can recognize from which genome or which taxon does this read come from. So in order to have the database, we need some genomes. So we have a library of genomes. Each one of them must have a tax idea. They can very well have the same tax. I mean, it's not like these have to be unique. You can have several genomes having the same tax ID. That's fine. But all of them must have some tax ID. That's the important thing. And it must be the NCBI taxonomy. That's what Kraken is using. And then we know once you have the tax ID, we can look up the branch. And this is exactly what we do in the first part of module 10. We do it in R with some functions that I made. But in principle, this is also what Kraken is doing. Once you have a tax ID, look up its branch, meaning all the ancestors above, right? In the taxonomy. Then also the Kraken software uses Jellyfish that we also used back in, I think it was in module 2 or 3 or something. So amazingly, the same software is used here again. But here we use it for counting k-mers in reads. And now we use it in a slightly different way, or Kraken use it in a slightly different way. It looks up all the distinct canonical 31 mers. So notice 31, that's the length of the k-mers, right? K equals 31, pretty long k-mers. And this is not from the reads, but from the genomes, right? From the genomes. You can use Jellyfish on the genomes as well. Any DNA sequence, right? And then look up all the distinct. So if the same k-mer is seen 2 or 3 times, we only store it once. So this is fairly straightforward. And remember that when you count k-mers in a genome, most k-mers of this length will be distinct. Very few of them will be seen 2 or more times, because in reads that is the norm, but not in the genomes, right? Because in the genome, all sort of most regions are unique, right? Only the repeated regions will contribute with 31 mers that you see more than once. So each k-mer that you collect now, we collect all the distinct canonical k-mer, and each k-mer is associated with what is called the lowest common ancestor taxon. And what on earth is this? We will see shortly. Here I have made an example. So let's say we now have 4 genomes we want to fill the database with. This is how we sort of build the database now. And all of these genomes has a tax ID, that's the blue numbers here. And these are at the species rank. It's not like all genomes have to be at the species rank, but in this example they are. Some are lower than species, they are strain, have a tax ID indicating a strain, but some also have higher. But for simplicity, let's say all our genomes are at the species rank. They all have a tax ID which is indicating a species in the taxonomy. Notice these two have the same tax ID, right? So these two come from the same species. But this one is another one, and this is another one. Now we can look up these tax IDs in the NCBI taxonomy, and we will find that all the species come from some genus, right? So this is the genus rank, and here are the tax IDs for these 2 genera. These are, I mean, these numbers are just random numbers I invented here now, so it's not taken from the, but all the tax IDs are numbers like this, right? Integers. And then, of course, all genera again belong to some family. And then again, all families belong to some orders, and so on and so on and so on. But let's stop here now. Let's stop here. But this continues up to the root, right? Order, then class, then phylum, kingdom, and so on and so on. So what happens now is that, let's say we scan through this genome here. Kraken starts by reading this genome here, collecting all the distinct canonical 31 mers from this genome here, and then assign each of these k-mers to some tax ID, and then it has to be this tax ID here. So let's say from scanning this genome, we have collected, let's say, 1,000 k-mers. Of course, much more than that in a genome, but let's think in that term now. So we have like 1,000 k-mers here associated with this tax ID 1001. Okay, done with genome number 1. Then Kraken goes to the next genome, do exactly the same thing, collects all the distinct 31 mares. And of course, this is now the same species, right? These two genomes are sort of similar to each other. Since they are from the same species, they must be quite similar, right? So I expect that many of the k-mers we collect from genome B has already been seen in genome A. So even if we collect, let's say we collect 1,000 more k-mers here, most of these k-mers have already been seen among these 1,000 here. So actually, from this genome B, we only store the new k-mers that we haven't seen before, right? And these are also associated with tax ID 1001. So actually what happens here now is just that this number here is is increased from 1,000 to a little bit more. Let's say, oops, I should have a pen here. Let's say to 1,200, something like that. Because 800 of these were seen before and 200 were new. So this number increased now. So we have 1,200 k-mers associated with this 1001 taxon. Then we go to the third genome over here and collect some new around 1,000 k-mers again. And this is a different tax ID. So what we now see is that, okay, but still some of these k-mers from genome C will also be shared with genome A or B. Right? Because even if this is a different species, it's still under the same genus, right? So they are sort of similar, but less, not so similar as A and B, but C is not that different from A and B. So still there will be quite a number of k-mers from genome C that we also found over here. And then, so let's say now that 800 of these are unique to this genome C, but 200 of the 1,000 we collected here are shared with this one over here. And that means these 200 they are associated both with this tax ID 1002 and also with this tax ID 1001. And what will Kraken do then? Well, then Kraken will say, put these 200 these 200 k-mers are not associated with any of these two, but with the one up here. So it will actually go to the lowest common ancestor of these two and say that these 200 k-mers are associated with 101 and not these down here. And what happens now is, of course, that 200 of these are now sort of moved up here, the 200 that overlap with genome C, right? So now we are back to 1,000 here, but these 1,000 are now unique to 1001 strain tax ID. 200 of them are found both in 1001 and 1002, and 800 are found only in 1002. And so on and so on. And then we move to the fourth genome over here and start collecting again. And let's say out of 1,000 here, we have almost all our, but still some will overlap with the ones over. So let's say 900 are unique here, and 100 overlaps with the others. And let's say these 100 are exactly 100 out of these 200 here. And that means that you get 100 up here, which is the lowest common ancestor now, And then we have to reduce the number here to 100 again. So this is how the picture looked like perhaps now after we have scanned these 4 genomes. So we can see that some or most of the k-mers are associated directly with the species down here, but some k-mers are associated with the genus up here because they are shared between different species under this genus, and some are even associated with the family up there. This family here, because these k-mers are shared between species of genera that belongs to this family. And this continues now up through the whole taxonomy, and you will find that some k-mers are so commonly found among all organisms that they are actually at the very top of the taxonomy. Some k-mers are found in all organisms, you could say. They end up at the top of the taxonomy here now. But most are unique to the lower ranks. And notice this one will have 0. And why will this one have 0 here? Because there are no competitors, you could say. There is only one species under this genus. For this one to have some k-mers associated to it, there must be some conflict, right, between species under it. But there is only one species under this genus, so there can be no conflict. Over here we can have conflicts, right? Because we have 2 different species. And the k-mers who are sort of shared between them end up here. Okay. After we have done this, we can actually think of the whole Kraken database as a big table, where we list all the distinct 31 mares in the first column, and then the associated tax ID in the second column. And then we can see most of the, and here we will have thousands upon thousands, millions perhaps, right? Depending on how many genomes we have looked into. Many millions, I suppose. So each distinct new 31 mare is associated with a tax ID. Most of them at the lower ranks, right? But some at the not so low ranks and some quite high up in the hierarchy. So this k-mer here, if it's associated with the family, it means it's found in different genera under this family. And so on. Yeah, and I should say that in reality, it's not stored as a table like this, because there is a much smarter solution to this, because this will be memory consuming. So, but at least for understanding the idea, it's smart to think in terms of a table. And remember, only the distinct k-mers are stored. So how many k-mers are actually stored? Well, it depends on the number of genomes, of course, but also how similar they are. Because remember that we only, when you collect k-mers from a new genome, you only collect the new k-mers that you haven't seen before. So if you add many genomes who are very, very similar to each other, the database doesn't grow very much after the first genome. Can you see that? Because only what is sort of unique to the new genome is stored as a separate row here. Okay. When it comes to classifying a read, how do we approach it? So now we have the database, and here I've sort of drawn a database again, and notice now I have replaced the single genomes with the sort of the species bubbles, right? So we had 2 genomes behind this species, and 1 here and 1 here. But now the species are the sort of entities, and the genera and the family, right? So we collect all the canonical k-mers from the read. So now we want to classify one particular read S, and then we collect all the k-mers. Not that many, right? Let's say 100 k-mers. Look them up in the database. Think in terms of the table on the previous slide. If you have 100 k-mers, you just go down the rows and find them. And then you'll see what is the tax ID they are associated with. And in this way, you can, for each tax ID, count how many k-mers this read contains that is associated with each tax ID, right? Then a classification tree, what the Kraken people call a classification tree, is the clade that involves all the taxa with k-mers and their ancestors. We will see that in a moment. So each taxon has, and then each taxon in that classification tree has a weight, which is exactly the number of k-mers that is assigned to it from the read, right? And then we classify to the leaf of the branch with the largest sum of weights. This is actually the whole procedure. So let's look at some examples again. First, let's say we have a read and we want to classify it, and it has 100 k-mers. Then we'll go into the table and look up, and we find that of these 100 k-mers, 50 of them are associated with this here, 1001. And the remaining 50 are here, 101. And that's all. These are the 100 k-mers for that read. Then we take out this branch here as the classification tree. And actually this extends up the tree, right? Because it involves also everything above here, but I haven't drawn it in, so let's stop here then, right? In this case now. But it actually involves everything up to the top. And then what does it classify to the leaf? Each taxon has a weight. Yeah, that's the numbers I wrote here now. So this taxon 101 has weight 50. This one has also weight 50, and so this one here has weight 0, right? No k-mers were assigned here, and all the ones above here will also have weight 0 now. And then we classify to the leaf of the branch with the largest sum of weights. Here there is only one branch, right? And the sum of weights is 0 plus 50 plus 50, which is 100. So this is the winning branch because it's the only branch. And that means we assign this read to the leaf of this branch, which is this here. This is the leaf, lowest, the lowest node in the branch, right? The lowest taxon. So the first read was assigned to this 1001. Let's imagine we have another read. Let's look at another read. And this one has also 100 k-mers. And let's change the color to something green. Now, these 100 k-mers are distributed like this. 40 of them are associated with this taxon. If we look up in the database now, 40 of these 100 are associated with this one. 20 are associated with this one. And 40 with this one. So this read looks a little bit like this species 1001, and it looks also partly a little bit like this 1002. And of course, it also looks a little bit like both in the sense that there are some k-mers here who are actually associated with the genus above them. And that's not surprising. When you have matching k-mers at two different species like this, you usually also have matching k-mers at the genus that they share, right? If they share a genus. So now what? What happens now? Now this is the classification tree, right? This is the classification tree now. And now we have two branches. And then we start adding. So everything from down to here adds 0. plus 40 here, plus 40 here, which means this branch has a weight of 80. The second branch also comes from the top with 0 weight. It passes through here with 40, and then it goes down here to 20. So it has 40 plus 20, which is 60. And then we can see it's this branch over here that wins, because it resulted in 80 k-mers. So again, this read is classified to this taxon here. Let's even have a look at a third example. And now I change my color to some blue here. Let's say we have a third read now. And this again has 100 k-mers. And how does this distribute? Well, 10 of them are here. 10 of them are here. 10 of them are here. And also 10 of them are here. And 60 of them are up here. Now this read is difficult, right? Because this has some k-mers that looks like this species, some k-mers looks like this species, some k-mers look... So this is a difficult read to classify. But how is it classified? Well, now the whole tree here is the classification tree. And now we have to add up the different branches. So first, above here, there is 0, right? Above this family. So the first branch is down here. And that will have a weight of 70, right? Because it's 60, 0 here, and 10 down here, 70, right? The second branch is going this route, and this will have 60 plus 10, which is 80. So we can see this one gets more weight than this one. And the third branch is down here, and it will have 60 plus 10, which is again 80. And now we don't have a winner. We have a draw. We have two species here with the same, and this over to the right here is not a winner. So that one we can forget about immediately. But what do we do now when we don't have a winner? Well, then Kraken will say that this read is not assigned to any of these two species because they are equally likely to be having this read. So then we assign it to the genus instead, the lowest common ancestor of these two. So this read will actually be assigned here. So you can see that in some cases, reads are not assigned to the species, but higher up in the hierarchy. And this can be even higher, right? Depending on how this read look like. If it's a read that contains k-mers that you find in almost all organisms, then it ends up very high up in the taxonomy. So this should now leave us with the possibility of understanding this figure here. Because here we have now the database. Right? This is the taxonomy tree of the database, or at least a small part of it. Here we now have the query sequence, the read. This is the read, the gray one here, right? And then from this read, we start collecting all these k-mers, right? These short ones here are the k-mers. And then we go to the database and look up where have we seen these k-mers before? And first, these white k-mers here, they are new. We haven't seen them before. So they are not assigned to any tax idea in the database. And this, of course, happens because the database doesn't contain everything in this world. We can have sequenced something new, right? A new organism that we have never seen before, and it will have some pieces that we haven't seen in our database. So the white reads here are unclassified reads. But we see quite many of them are blue, right? And that's because they match this taxon here, the blue taxon here. 10 of the reads matches the blue taxon. One of the reads matches this purple taxon here, or I shouldn't say matches, it's associated with, right? So the blue are associated with this one, the purple is associated with this one, the orange ones are associated with this one, and so on, right? One red associated over here. And then we can see from this picture here that the classification tree is now containing this part here and this part over here. And if you look, that's exactly what you see over here. We have now taken out the purple node, the blue, and the orange, purple, blue, orange, right? And the purple, black, red, purple, black, red. So these are the two parts of the whole database taxonomy that we are now considering, right? And also notice the numbers inside each circle here now is actually the number of reads that were associated. There was one purple read associated here, right? That's why we have one here. 10 are blue, right? 10 of these up here match blue, so that's why we have 10 in here. And 4 were orange, right? So that's why we have 0 in this one, but 1 down here in there. And now we just add up the different branches, right? 1 plus 0 plus 1 is 2. 1 plus 10 plus 14 is 15. This is the winner. This branch is the winner, and then we assign to the leaf of that branch, the lowest. So that's why we now assign to this taxon here. The output from Kraken, what does it look like? Well, we have seen that most reads are classified to the lower ranks, right? That's reasonable. But some reads are classified to higher ranks in those cases where we have no winning path. If there is a draw between 2 or more paths, then we jump to the lowest common ancestor, higher up in the taxonomy. So some reads will be classified here. The tax count that is in this report file from Kraken, the tax count for each taxon, that's the number of reads assigned directly to that taxon. Directly to that taxon. The clade count, which is another column in the same table, there is also a clade count value for each taxon. That's the sum of all reads assigned to the taxon and all those taxa below it in the taxonomy. So these numbers grow the higher up in the taxonomy you get, because it's sort of cumulative, right? All the read counts for the species are summed and added to the genus above them. And then all the read counts for the genera are summed and added to the family above them. And then the family values are added to the order, and the order values to the class and class value, and so on and so on. So the numbers get bigger and bigger and bigger the higher you get up in the taxonomy. So actually at the root, the clade count for the root is actually the total number of reads in the whole sample. All the reads that has been classified end up at the root in this column. But this column is what is classified uniquely to each taxon itself. Okay, let's move on and have a look at this bracken idea, because this is very closely associated with the one we just saw. So it's about post-processing these Kraken 2 results. And let's remind us of the Kraken database, sort of. This is how it was like with the species here, and then the genera here, and the family, and so on and so on. First, we run the Kraken 2, and we saw that some of the reads may be classified to higher rank. Most end up here, but some will end up here, and even here, and even higher up. The bracket is meant to reassign these reads to the lower ranks. And why is this important in some cases? Well, this reduces the bias on the abundance estimates for the lower ranks. Because there are some biases here, and this bias is due to the database having a biased sample of genomes. Let me try to illustrate it. I'm not sure how easy this is to understand, but let's say now that in our sample that we are now classifying, there are actually 1,000 reads that comes from this species here. And there are also 1,000 reads coming from this species here. This is sort of the truth, right? But this is invisible to us, but I note it here now. And then we let Kraken do the job. And what happens? These 1,000 reads here that should be classified 2003, let's say that 990 of them end up down here. And 10 of them are classified up here. Because there are some reads, even if they come from this organism here, they could easily also come from one of these over here, right? They look like they could just as easily have come from one of these, and then we have a conflict, and then it ends up on the top here. Then what about this 1,000 over here? They will probably only like 700 of them will end up here. And why is this number so much lower? Because this species here has a competing species over here, the 1,001. So many more of the reads that come from 1,002 look like they could have come from 1,001. So 300 will end up here, is my sort of guess now. And this is this illustrates the point that this species over here, it's sort of alone in the database, or its nearest neighbor or nearest relative is quite far away, right? But this species over here has a very close relative also in the database. So many more of the reads that comes from 1002 will look like they also could easily come from 1001. So many more of them end up in the level above. And now if you start to only count the values that are assigned to the species, it looks like 1003 is more abundant than 1002. Can you see that? 990 reads over here, but only 700 here. But in reality, it's the same. They are equally abundant, but Kraken will not recognize this because of this lowest common ancestor way of reasoning, right? Because many of these are assigned up here, not so many of these other were assigned up here. So you can say 1003 only lost 10 reads to its relatives, but this one lost 300 because it has so many, it has a closer relative. And this is exactly the point that is made in this paper as well. It says, therefore, any assumption that Kraken raw read assignment can be directly translated into a species or strain level abundance estimate is flawed. You cannot just look at the output from Kraken and think that these reflect the actual abundances. And if you read the rest of that sentence, you said, if you ignore the reads at the higher levels, that means these and these. If you ignore them, you will grossly underestimate some species, and that's this one, right? This is underestimated because it has a neighbor in the database. And think about this. This is because we added this genome to the database. If we had left this out from the database, then this would not have happened.
This would not have happened. So this only happens because we added this to the database. And of course, this is not how the method should work in a sense that it depends on what you have added to the database. But this is how it is. And there's actually no way around this because we add to the databases the genomes we have, right? But in some branches of the biology, we have done a lot of sequencing, while in other branches, we have done almost no sequencing. So we don't have very many genomes to add. But some places, for instance, E. coli, there are tens of thousands of genomes of E. coli that we have sequenced. And we can add tens of thousands genomes under one species, right? But in other branches, we have perhaps only one genome for the whole species. So this will create biases. And that's what Bracken is trying to help us with now, to get more reliable abundance estimates for these lower ranks, for the lower ranks. So how is that done? So imagine now we are in this setting here, and here we have actually just narrowed it down to one genus with 2 species under, right? So let's look at this tiny little part of the database. So we want to reassign all the reads to the species rank. Let's say we want to do that now. And then a number of reads has been assigned to the genus. Right? They are here. How should we distribute these down to the 2 species below? That's the question we have to sort of face now. Should we just split it in 2 and say, okay, half of these reads go down here and the other half goes down here? Is that reasonable? That's perhaps the first you would think, right? Isn't that reasonable? Well, if you start thinking about it, it's not reasonable. Because behind this species here, we can have 10 genomes. Behind this one here, we can have only 1. This could easily be the case, right? We saw in the previous example that we had 2 genomes here and 1 here. So it's not like you can just automatically divide this in half, because it must depend on some probability that these reads actually came from here, or well, whether these reads actually came from here. So we need some probabilistic approach to this. And this is where the Base Theorem comes into play. This is a formula you should actually recognize, I think, from statistics. And what does it say? What is it that we are focusing here now? This probability here on the left-hand side, what is it? It's the probability that a read should be assigned to S1 given that it was assigned to G1. That's what we want to compute in a sense. The probability that we have a read up here, what's the probability that it should be actually belong down here? And the other probability is on the other branch, right? So it's S2 instead of S1. So it's a probability of assigning it to, or actually the read coming from S2, given that it was assigned to genus 1. So if we can compute these 2 probabilities here, then we can assign the reads like this. Take the whole number of reads that you have up here and use these probabilities just as fractions, right? So if this is 0.7 and this is 0.3, then 70% of the reads are assigned down here and 30% down here. If they are, if this is 0.5 and this is 0.5, then we split it equal amounts, right, in each direction. So these 2 probabilities here we have to compute now or estimate in some way, because this gives us directly how we should, which proportion of the reads should be assigned to each of these 2 species. And then you can see from the base formula here that in order to compute this probability, and the same over here, we have to compute these three probabilities here. And why can't we compute this directly? Well, it's impossible because then, or if we could have then this would be really simple. But these probabilities we can actually compute, and that's why we need this base formula in this case. But remember, it's these probabilities we are interested in at the end of the day, these two, right? So let's see now how we can compute this one here, and then of course this one will be exactly the same because you can see it's the same formula. It's just S2 instead of S1. Yeah, and I should also mention, of course, that these reads are now added to this species in addition to those that they got from Kraken, right? Because they already have some reads assigned. So it's only the extra reads that come from up here we are talking about now. How do we estimate these probabilities? Well, the first one is super simple. The probability of actually the read being assigned to the genome, the genus is 1, because we only consider reads that are assigned to this genus now. So actually the denominator here is super simple. So it's only the two probabilities up here we need to actually compute. And the first one, this conditional probability here, that's the probability that a read end up in genus 1, given that it originally belongs to this species, right? And how do we estimate it? How do Bracken estimate it? Bracken do it like this. Collect all possible reads of length r from this species. So it dives into the Kraken database, collects all the k-mers, or actually collects the genome that is in the database, and then cuts it into reads of length r. So it's actually r-mers in a sense. And then each of these reads are classified the same way as Kraken is doing it, as if it was any read, right? And then you will see some of these reads end up, of course, most of them end up in S1, but some will probably end up in S2, and some it is G1, etc., etc., right? And then actually the fraction ending up in G1 of these reads is the estimate of this one. So how likely is it that a read coming from this originally will end up being classified to the genus above by Kraken? That's what we are finding out here. So this is actually about using the Kraken to a lot on all possible reads from this genome. And then, of course, if you replace S1 with S2, it's exactly the same procedure again. This probability here, probability of read coming from S1, unconditionally, that's also possible to estimate in a similar way, actually. But now, instead of collecting all the reads from S1, we collect all the reads from all the species under this genus. And then we let Kraken classify all these reads again and see where they end up. And then the fraction of these reads that end up in S1 is the estimate of this. So you can see that this is reflecting the number of reads that you can generate from all these genomes that are unique to this species here. While up here, it's sort of the other way around. It's all the reads you can generate from one particular species that are not unique to that species, that are shared with the others and therefore end up here. So, and then of course, once we have these three probabilities here, we can compute using the Base Theorem up here. So now we have a number for all the three here, and then we get a number for this one. And then we can do the same for all the species, right? And this is done by Bracken when you build the Bracken database, actually. Most of this job. So what is the output from Bracken then? Well, again, it's a report file with a sort of a table in it. And the original clade counts that were in the Kraken 2 results are also displayed in this result table. And then it all displays how many additional reads was now assigned to each species. And then, of course, the total count by adding the original to the added ones, which is the final abundance estimate for that species. And we should note that, of course, most reads are already assigned to the lower ranks. So using Bracken will only modify these results. And if you look at the higher ranks in the taxonomy, the Bracken will not change the results very much there. If you try to reassign with Bracken at, let's say, the phylum level, then almost nothing changes, because already there almost no reads are assigned above phylum, right? But at the lower ranks, it may change quite a lot. And these are all usually what we are more interested in, the lower ranks, species and so on. So that's why this Bracken has some relevance to us. But remember this, if you are only interested in very sort of high up in the taxonomy, you can just as well skip the whole Bracken, because it will probably not change the results from here at all. You can look at the clade counts directly from Kraken.
Okay, let's have a look at the OPAL paper. And here it is. And this is about assessing taxonomic metagenome profilers. And metagenome profiler is a tool that do taxonomic classification and then predict the abundances of all the taxa in there, right? So that's what we are looking at, assessing this. And let's scroll down to this section here called metrics and accompanying visualizations. So the very first thing we look at is this preliminaries. For R, a particular taxonomic rank, consider a rank in a taxonomy, and we now stick to the species rank, but this could be easily done for all ranks, right? So if you classify it to the species, you consider the species rank, but if you classify it to genus, you consider the genus rank, and so on, right? So R is used to sort of indicate any rank then, but think of it as species now. Let XR be the true bacterial relative abundances at this rank given by the gold standard. So we need a gold standard, of course, right? It's impossible to know how well these profilers or these taxonomic classifications are unless you have some truth to compare it to, right? We need a gold standard. So here I have a gold standard. And this is a very small metagenome because it has only 3 different taxa, 3 different species. And I denote them by tax ID here instead of name. I think that's better because names are shaky, right? Tax IDs are the more accurate way of organizing them, displaying them or naming them. So we have relative abundances here, the true abundances. This is what we would try to predict, right? These 3 only, and 50% of this one, 30% of this one, 20% of this one. Here I have written it in a vector like they say here in the paper, right? XR is now this vector here. And the numbers here are simply row numbers or indexes, right? So it's taxon number 1, 2, and 3. Value number 1, 2, and 3. 1, 2, and 3 here. Okay. And then we need, of course, a prediction. So XR star is a vector of predicted bacterial relative abundances for the same rank, of course. So let's add some predictions. And here they are. We add them as a new column to the same table. And then we see a couple of things immediately here. First of all, we notice that in these predictions, there were 3 new taxa here that were not originally in the gold standard. So the table grows.
And how do we make this table? Well, we had the gold standard table, and then typically we have a new table with the predictions on also tax IDs, and then we join these two tables by the tax ID. So we make sure that the rows that correspond to the same tax ID are matched against each other, right? And that's why I called it a joint table. This full is the joint table. We will do this in the exercises. We also notice these are not relative values like it is here. These are probably read counts or something. We should turn this into relative values. We will see. And also, we see there are some holes, of course, in the table, because these three taxa were not in the gold standard, so there are some empty cells here. And also this taxon, 1002, were never predicted, so it's an empty cell here as well. So what we have to do now is to make sure that we have these relative values in the gold standard and also relative values in the predicted abundances. And also we have to fill in this empty cell. So the very next thing we do now is to compute the relative values here. And how do we do that? Well, if you go back to the previous, if you sum all the values in this column, you get a total sum. And then you take all the elements and divide by that total sum, of course. So then you have the relative values. And as if you notice, the sum here is 1000, and that's why the numbers here are pretty. And then we fill in with zeros in all the empty cells, because abundance being absent means that the abundance is actually zero. So in this case, missing value is the same as zero, because it's sort of a count, right? You count reads or whatever, and if it's not counted, it means count zero. And here we now have the corresponding vectors XR and XR star. These are just columns, right, of this table. Okay, let's go back to the paper here. The next, or the very first thing we want to do is to assess the profiler based on presence or absence of the taxa. And in order to do that, we need to decide what is present and what is absent. And that's what this formula here, or this metric here, is all about, the support. The support of a vector, in this case the gold standard abundance vector, the column, the support of it, what is it? And let me read out loud. The set of indexes I such that the abundance number I is larger than zero. That's what this expression says. And notice the threshold 0 here, right? The indexes I such that the abundance is larger than 0. If we go back to our small example, what does the support for this vector look like and the support for this vector look like? Here they are. The support for this XR vector is the set 1, 2, and 3. So these are the indexes, the row numbers, where the corresponding abundances in this column is larger than 0. Right? This is larger than 0, this is larger, but this is not larger than 0 because it is 0. Right? So that's why the support of this one is 1, 2, 3, because it's the first 3 elements that are larger than 0. And we see the support for the predicted vector over here is this, 1, 3, 4, 5, 6. Not 2, because 2 is 0 here. Right? So this is the support of these two vectors. And then from these supports we can compute our old familiar stuff, true positives, and false negatives, like this. And notice the true positive, that's the intersection between the two supports and the size of that intersection. Right? So what we actually do, let me jump one. We take the support from this one, 1, 2, 3, and the support for this one, 1, 3, 4, 5, 6. What is the intersection between them? Which elements in this is also an element in this? It's 1 and 3. And the size of that is 2, because there are 2 elements, right? So here we have the true positive, 2. Two true positives, and we can see it directly from here, right? Because this is predicted and it's also true. This is predicted positive, and it's also true. So there are 2 true positives. The false positives, that's the intersection between the complement of this support, right? This is what this means. The complement of the support. And what is the complement? Well, if you have the support up here, the complement is all the indexes that is not part of this support. That's the complement, right? All the indexes, say 1, 2, 3, 4, 5, 6, 3 of them are in the support, and then the 3 others are in the complement of the support. And the same down here, right? Here is the support, and the complement is then the element which is not in the support. So if you take the intersection between the complement of the gold standard support and the support of the prediction, that means the intersection between this set and this set, and you can see 4, 5, and 6 are in both. So the size of that intersection is 3. And the same for the false negative here, and you get size 1, because there's one element here which is also part of this here. Yes, so true positives, false positive, false negative. I mean, this way of writing it is a little bit, I feel, unnecessary mathematical, because it's so much simpler to see it from the table, isn't it? True positives, those who are present in both, right? False positives are those who are present in the prediction but absent over here. That's these 3. And the false negatives are the reverse. They are present in the gold standard but absent in the. So that's so much simpler. Okay. Once we have these 3 here, we can compute the good old precision and recall. And of course, these people here, they have invented some new name for precision and recall. They call purity, which is the same as precision. Or specificity, they say, and this is dead wrong. This is not correct. Precision is not the same as specificity. You can look up specificity; it's not the same. But and they use it. I don't know why they have to invent a new name for it. It's a rather stupid thing to do, I would say. Why don't use precision that we know everyone knows what it is? And here it's a formula, and we recognize the formula, right? You should have seen this before. They also call completeness, that's recall, right? Or sensitivity, and that's correct. Recall or sensitivity, they are synonyms, meaning the same thing. And here you have a third synonym now. If you want to make yourself important in this world, invent new words for old ideas. And here we recognize the formula. So if we go back here and compute based on these numbers here now, we can compute precision and recall. Then this is the precision, quite bad here. Recall, also not very good. We would like both of them to be close to 0, right? They also introduced the Jacquard Index here. First of all, this F1 score, I don't mention it. You can see it's just a product. It's a way of combining precision and recall into one single number. Have a look at it if you like. But more interesting, or I would like to mention this Jacquard Index, because we have talked about Jacquard indexes before when we talked about the mesh distances. So here is how you can compute the Jacquard Index. And here they use this very mathematical formula, I would say, unnecessary again, because what you see in the numerator here is actually the true positives. And what you see in the denominator here is actually true positives plus false positives plus false negatives. If you add them all three, then you get this one here. And actually, it's I would say it's easier to look at it over here, because Jacquard Index is simply the size of the intersection between these two columns. The present stuff, right? That's this one, and divided by the size of the union. So the size of the union is actually the number of rows you have, right? The union, that's the total number of taxa in the whole data set here. And then the size of the intersection is the 2, because it's these 2 rows here, right? So it's 2 divided by 6 then. Notice that the reason why, and this is also quite poor, right? We would like this to be close to 1 as well. Then the prediction is very close to the gold standard. And the reason the prediction is now very different from the gold standard is partly due to these 2 here, very much due to these 2 here. And this questions again this threshold of 0. If we scroll back a little bit here to that support, right? This here. We say that it has to be larger than 0 to be present. Anything above 0 is present. Is that really the case? I mean, these are very small values. I would say that when you have this low abundances, these taxa are hardly present in my data. This could easily be due to some noise here, right? The reads have been misclassified into these 2 taxa. A few reads, right? Few reads only. So when the abundances are this low, I could easily call this absent. So actually using a threshold at 0 is a little bit sort of extreme. I would at least allow this to be a little bit above 0, so that these 2 are actually also are not part of the support here, right? If you take 5 and 6 out of the support here and then compute over again, you will see that the results are not that bad after all. But they become bad because of these 2 here. Okay. Let's look at abundances instead, because then we don't need to don't need these thresholds, and that's an advantage of abundance. When we compare the abundance, how do we compare the abundances? Well, they suggest we use the L1 norm, and here is the formula for it. And what is it? Well, sum over all the indexes the following. Take the abundance from the gold standard, number I, subtract the corresponding abundance number I from the prediction, and take the absolute value of this, and then do this, sum this over all indexes. That's the L1 norm, which is also the same as Manhattan distance. We talked about Manhattan distance in another context, and it was about this pan matrix trees. It was actually the same formula. I didn't present the formula then, because then all the values were either 0 or 1. Here we have abundances, which are decimal values, right? But if the values are 0 and 1, you can express this in a different way, but this is the general formula for L1 norm or Manhattan distance. And here is how we actually compute it now. So here I've written the formula again in a slightly different way. First of all, I specify that I goes from 1 to 6, since we now have 6 indexes, right? So we sum over all indexes, and what do we do inside here? We take abundance number I, and I use the brackets like we do in R. Abundance number I from this column minus abundance number I from this column, subtract them and take the absolute value. And that's exactly what we do over here. So notice we start with I equal to 1. First row, we look at the differences. 0.50 minus 0.60, and then take the absolute value, so you get 0.1. And then plus, we go to the second row, minus 30 minus 0, 0.30 minus 0, An absolute value becomes 0.30 here, which we add to the first one, and then we proceed down the table like this, right? Looping, you could say. But you don't really need to do the looping in R, but that's another story. But in principle, it's a looping, right? You compare element by element by element here. And of course, if the abundances here were exactly the same as the abundances here, then all the differences will be 0 and the total sum will be 0. So if you have a perfect prediction over here, then the L1 norm becomes 0. That's the best you can have, right? The Manhattan distance of 0 means there is no distance, right? There is no difference between them. They are identical. But on the other hand, what is the worst possible distance you can have? How big can it be? Let's imagine that the prediction had zeros in the first 3 rows and then some positive values in the last 3 rows. So that you compare a value here to 0, compare to 0, compare to 0, and then compare 0 to this, compare 0. Then you have the maximum distance, which is the sum of the values in both columns. And we know that the sum of the values in each column is 1, so the sum of both is 2. And that's actually the largest distance you can have here, 2, as long as you have these relative abundances. Then the paper introduces the Bray-Curtis distance, and this is really surprising to me. And here's the formula for it. And have a look at this formula. See that the numerator here is exactly the same as the L1 norm up here. Can you see that? 100% identical. And what is in the denominator here is the sum of all the gold standard abundances. But that's 1, right? The sum in this column is 1. And then the sum of all the predicted abundances. Yeah, but this is also summed to 1, right? This was required. This was required a few lines above here, that we should do this. So what you actually do here is you take the L1 norm and you divide by 2. 1 plus 1. So what's the point of that? What's the point? I mean, if you have computed the L1 norm, then you compute it again and divide it by 2. I mean, that's the same thing, right? Whether you compute it here or compute it again and divide by 2, what's the point of that? So instead of having a value that goes between 0 and 2, you have a value that goes between 0 and 1. But these two will measure exactly the same thing, right? So it's pointless to have them both. You can choose one of these two, but not include them both. I don't understand why they have this both in here, as long as they do this. I would not have done that. Choose one of them. And then finally, I will just say a few words about weighted Unifrac distance. There is no formula for it here, and that's a good reason for why it's not a formula, because it's too complicated. But I can I can try to illustrate the idea behind a weighted Unifrac distance. So with the L1 norm now, or Manhattan distance, or the Bray-Curtis for that matter, we now just compare the values between the predicted and the true abundances, right? And it came out, well, not super bad, but not super good either here. And why did it come out with this large L1 norm? Well, very much has to do with this row here, row 4, and row 2, right? Because here in row 2 we have taxon 1002 is actually quite abundant, but we predict it not to be there at all. It's a big miss here, right? And here in row 4 we have a big miss the other way. This taxon here should be not in here at all, abundant 0, but we predict it to be quite abundant. So you can see this one this miss plus this miss is 0.49, right? Almost, yeah, majority of this due to these two misses. But what now if this taxon here is a very close relative to this taxon here? It's not the same since there are two different tax ideas, but this could easily be a species which is very closely related to this species here. So that actually we claim that these reeds are from this species, but we are now confusing it with this species here, and we should actually have assigned these up here. So if that is the case, then the picture is not as poor as it looks like now. Do you agree? You missed, but you missed only with the neighboring species, you could say. And that is exactly what the weighted unifrac distance is trying to include into the distance measure, right? That we have to actually look at the tax ideas here and see which of these taxa are closely related and which are more distant related. And then we should take that into consideration in a way that makes these differences a little bit more reasonable. So a weighted unifrac distance is more cumbersome to compute because then you also need sort of a phylogenetic tree for these taxa, saying something about which is closely related and which is more distant related. And then you have to use this as a weight when you compute these differences here. It's actually sort of an extended Manhattan distance in a way, but with some weights. So for instance, this difference here and this difference here will be weighted down and not count as much anymore if this taxon and this taxon is very closely related. But if they are not, if they are very distant related, then they are perhaps weighted up, so it becomes even worse than it looks like now. But that's the idea of the weighted unifrac anyway. And then I think we are happy. This alpha diversity metrics we don't talk very much about because they are not really very useful for what we are doing here. And beta diversity metrics, that's exactly what we have been looking at now. Both the L1 norm, the Bray-Curtis, and the weighted unifrac are examples of these beta diversity matrices. And when it comes to visualizations, we will actually look at that in an exercise where we plot what we call a stacked bar chart. So I will not use the paper for that. So I think that's what we need.